Imagine having some of the biggest computers on the planet united with one aim: to work out the best way to treat a tangle of fine blood vessels or a ballooning artery that are threatening to kill a patient with a stroke. That's the promise of Genius, an Anglo-American project supported by the Engineering and Physical Sciences Research Council in the UK and the National Science Foundation in the United States. Genius aims to harness global computers to support the treatment of blocked and leaking blood vessels in the brain through the use of advanced simulation techniques and by providing stunning images of what goes on inside a patient's head. Cardiovascular disease is the third biggest cause of death in the developed world, and cerebral blood flow behavior plays a critical role in the understanding, diagnosis, and treatment of this disease. Using a computer to investigate the way to treat a patient so the best approach can be honed offers to revolutionize the way clinicians plan courses of treatment. Life-threatening conditions where the blood vessel plumbing of the brain goes wrong, such as aneurysms and arteriovenous malformations, no longer require a hole to be drilled in the head so a surgeon can attempt to repair the damage. Some malformations in blood vessels can be treated using a technique called embolization, where a glue is used to reroute and correct blood flow. Aside from a surgeon's own experience and intuition of exactly what to do, there are no imaging techniques which can show clinically important blood flow properties such as the velocity, pressure, and stress. The Genius project aims to provide this information so that doctors can work out where an aneurysm might form, a weak point in a blood vessel that might pop, and to study the best way to stop that potentially fatal effect. To model blood flow through the entire brain in a way that's quick enough to be practical, the Genius project uses the so-called lattice-Boltzmann technique, but does it in such a way that only the blood vessels are considered, saving valuable time and computing power. The simulator, called HemLB, has been tested on various supercomputers and can work on a single machine or multiple machines in a distributed fashion. It's shown excellent scaling up to thousands of cores. In order for clinicians to see what's going on, the simulator harnesses the kind of computer tricks seen in animated films, such as ray tracing, to show the blood flowing through the fine lattice of blood vessels in the head. It's taken a blend of innovative software and hardware infrastructure to efficiently run the simulations on computers worldwide. What's remarkable is that doctors can tweak the simulations in real time using a method called computational steering. For example, with the HemLB simulation, the clinician can do this to gain greater understanding of the patient's condition. Doing this while the simulation is running saves time and money and means that changes to the simulation's parameters can be investigated in real time. The interactive nature of our simulations means that we require access to high-speed, low-latency network connections in order to do real-time work. To bring global computing resources as close as possible to the operating theatre, we've worked with Janet UK to deploy dedicated network connections called LightPaths, linking the NGS and TeraGrid directly to the Genius workstation for use by doctors in the National Hospital Angiography Suite. To make it easier to process data, run simulations, interact with and visualize the blood flow in a patient's head, we've developed a desktop client to allow the clinical user to easily manage their simulations. A typical workflow comprises the following stages. First, the user selects a pre-reserved HARC time slot on one or more supercomputers. Next, data on the blood vessels is collected from the patient with an X-ray scanner using a technique called 3D rotational angiography at the National Hospital. The data is anonymized and then uploaded into a DICOM repository on the LightPath network. Using a PC in the angiography suite control room, the clinician downloads the patient's data from the repository. The downloaded data is then used to construct a model for HEMEL-B. The model is uploaded to a GRID FTP staging post server. The simulation is then launched using job submission services provided by the application hosting environment. When the HEMEL-B simulation begins, the doctor can visualize and interact with the running simulation on their local machine. To make heavyweight computation available in a way that can give doctors help when they need it, we've deployed a sophisticated grid computing infrastructure, advanced reservations and emergency computing, and sophisticated ways to link the doctors to global computer resources. These real-time simulations of the workings of an organ in a patient represent a novel concept in medicine, one with huge promise. However, it requires a great deal of testing and validation, especially when used in real time during surgery. We've demonstrated that this infrastructure is a necessary prerequisite in achieving the crucial medical factor of timeliness of results, and we anticipate that this approach will lead to heavyweight computer resources being available to help doctors to save lives.